Picture the birth of our sun, an event that unfolded in the distant, swirling mists of the past, some 4.6 billion years ago, deep within the stellar nursery of a solar nebula. These nebulae, vast, cold clouds of gas and dust, are the cradles of stars, the places where the very lights that fill our night sky first ignite. The stars they birth may appear to our eyes as simple, massive balls of fire, but inside them, a delicate and precise cosmic ballet is at play. Gravity, the relentless inward pull of matter upon itself, is constantly trying to crush the star, but this is perfectly balanced by the immense outward push of thermal pressure, generated by the thermonuclear fusion raging in the star's core. This state of equilibrium, known as hydrostatic equilibrium, is what keeps a star like our sun stable and shining for billions of years. But this balance is not eternal. When a star's fuel begins to run low, this delicate dance falters. Gravity begins to win, and the star's fate is sealed. It will either expand into a bloated red giant or collapse under its own weight into a white dwarf, a neutron star, or, in the case of the most massive stars, into a black hole, a point of infinite density from which not even light can escape. This entire cosmic drama, from the gentle birth of a star to its violent death, is governed by just a handful of fundamental forces. Four, to be exact, in addition to the familiar forces of gravity and the thermal pressure driven by electromagnetism. There are two other forces that operate on the subatomic scale: the powerful, strong nuclear force, which binds the nuclei of atoms together, and the elusive weak nuclear force, which governs the process of radioactive decay. These four forces, in their intricate interplay, shape everything in our universe. The history of science is, in many ways, the story of our gradual discovery and understanding of these fundamental forces, and each time we have uncovered a new force or a new aspect of a known force. It has not just reshaped our scientific models, it has reshoken civilization and redirected the very course of human history. Isaac Newton's revelation of the universal law of gravitation in the 17th century was not just an academic achievement. It provided a rational, predictable, and mathematical framework for understanding the clockwork motions of the heavens. This new mechanical worldview set the stage for the rise of machines, the development of engineering, and ultimately fueled the engines of the Industrial Revolution. Then, in the 19th century, a new force was tamed. The brilliant, intuitive work of Michael Faraday and the mathematical genius of James Clerk Maxwell unveiled the deep, intimate connection between electricity and magnetism. Their insights did not just lead to a deeper understanding of nature. They lit up our cities, powered our motors, and gave birth to the age of instant global communication through the radio and the television. At the dawn of the 20th century, Albert Einstein, with his groundbreaking equation, E equals mc squared, unlocked the secret of the immense energy that fuels the stars and, in doing so, revealed the awesome power hidden within the nucleus of the atom, the power of the strong and weak nuclear forces. And then, in the 1920s and 30s, a new generation of physicists, Schrödinger, Heisenberg, Dirac, and their peers cracked the code of the quantum world. They discovered a new set of rules that govern reality at the smallest scales, and in doing so, they sparked the high-tech revolution of the late 20th century, gifting us the lasers, the transistors, the supercomputers, and the internet that are now woven into the very fabric of our everyday lives. Over the last century, as our understanding of these forces has deepened, physicists have uncovered two profound and universal traits that they all seem to share. The first is that at the most fundamental quantum level, Each force is transmitted, or mediated, by its own specific type of particle. The electromagnetic force is carried by particles of light, the photons. When two electrons repel each other, they are not just acting on each other at a distance, they are exchanging virtual photons, like two skaters on an ice rink pushing each other apart by throwing invisible bowling balls back and forth. Similarly, the weak nuclear force is carried by the massive W and Z bosons, and the strong nuclear force, the force that binds quarks together inside protons and neutrons, is carried by particles playfully called gluons, because they act as the cosmic glue that holds the nuclei of atoms together. By 1984, all of these force-carrying particles had been discovered and thoroughly studied in our particle accelerators. The only one that remains elusive is the hypothetical particle of gravity, the graviton. The second shared trait is that the way a particle interacts with a force is determined by a specific charge that it carries, just as a particle's mass determines how strongly it feels the pull of gravity, and its electric charge determines how it responds to the electromagnetic force. Particles also have a weak charge and a strong charge that determine how they interact with the weak and strong forces. But this deep and beautiful picture is also profoundly incomplete. It raises a host of new and even deeper questions. Why these four forces, and not some other number? Why do they have the specific strengths that they do? Why are the strong and weak forces confined to the tiny realm of the atomic nucleus, while gravity and electromagnetism have an infinite reach? And why do the fundamental particles of matter, the quarks and the leptons, have the specific and seemingly random masses and charges that they do? These are not just academic questions. The very existence of our universe, with its stable atoms, its long-lived stars, and its complex chemistry, depends on an exquisite and delicate balancing act between these forces and these particles. A tiny change in any one of these fundamental parameters would result in a universe that is sterile, chaotic, and lifeless. This is the profound puzzle that led Albert Einstein to dedicate the last 30 years of his life to a single, audacious goal: the search for a unified field theory. A single, elegant framework that would unite all the fundamental forces of nature into a single, coherent whole. He dreamed of a concise, powerful equation that would allow him, as he famously put it, to understand the mind of God. Einstein, for all his genius, did not succeed in this quest, but the dream of unification did not die with him. It has become the holy grail of modern theoretical physics. And today, many physicists believe that we are perhaps on the verge of realizing Einstein's dream, that we are closing in on a theory that has the potential to unify all the forces of nature. A theory that could answer our deepest questions about the cosmos. A theory that has been given a strange and beautiful name: the theory of everything. The quest for a unified understanding of the cosmos is not a new one. It is a thread that runs through the entire history of human thought, from the earliest myths to the most advanced scientific theories. The night sky, with its dazzling and seemingly chaotic tapestry of stars, has always invited contemplation. It urges us to ask the big questions: is there a hidden order, a higher plan, that governs the universe? Or are we merely adrift in a meaningless, aimless cosmos? The ancient Greeks were among the first to systematically seek a rational order in the apparent chaos of the natural world. Philosophers like Thales and Anaximander sought a single, underlying arch, or principle, from which all of a reality could be derived. Aristotle, in his grand systematic philosophy, proposed that everything in the terrestrial realm was composed of just four fundamental elements: earth, air, fire, and water, governed by the principles of motion and change. It was a powerful and influential picture, but it struggled to account for the immense complexity and diversity of the world around us. Other Greek thinkers, like the atomists Leucippus and Democritus, offered a different and remarkably prescient idea that everything is made up of invisible, indestructible, and eternal atoms, moving in an infinite void. They even believed that the rich diversity of the natural world could be understood through the mathematics of combination and arrangement, a precursor to our modern understanding of chemistry. For centuries, these philosophical debates remained largely speculative. It was not until the Renaissance and the scientific revolution that a new, more powerful method for seeking order in the cosmos emerged. The Italian astronomer and physicist Galileo Galilei was a pivotal figure in this revolution. He did not just philosophize about the heavens, he observed them. With his improved telescope, he peered deeper into the vastness of space than any human had before, discovering the moons of Jupiter, the phases of Venus, and the mountains and craters on our own moon. His meticulous observations provided powerful empirical evidence for the heliocentric model of the universe, a model that placed the Sun, not the Earth, at the center of the cosmos. This was a direct challenge to the established geocentric worldview of the Church and of Aristotelian philosophy. And Galileo's courageous defense of his findings ultimately led to his tragic house arrest. But the seeds of a new scientific cosmology had been sown. Galileo's emphasis on observation, on experimentation, and on the mathematical description of nature laid the foundation for modern physics. He died in 1642, a man in despair. But his legacy was to be carried forward by a child who was born in that very same year, across the English Channel. His name was Isaac Newton. Building upon the meticulous astronomical observations of Johannes Kepler and the foundational work on motion by Galileo, Isaac Newton, in his monumental work, the Philosophia Naturalis Principia Mathematica, published in 1687, achieved the first great unification in the history of physics. He showed that the same force that causes an apple to fall from a tree is the very same force that keeps the moon in its orbit around the Earth and the planets in their orbits around the Sun. This force was gravity, and Newton described it with a single, elegant, and universal law. It was a law of breathtaking scope and power. For the first time, the heavens and the earth were united under a single mathematical principle. The world, it seemed, was a rational, predictable, and clockwork universe, governed by a set of immutable mathematical laws. Newton's laws of motion and his law of universal gravitation were so successful, so powerful in their ability to explain and predict the motions of the celestial bodies, that they became the very paradigm of what a scientific theory should be. A key characteristic of Newton's laws was their uniformity. They applied equally to the small and the large, to the terrestrial and the celestial, and for over 200 years, they reigned supreme. Their power was dramatically demonstrated in the 19th century with the discovery of the planet Neptune. Astronomers had observed that the orbit of Uranus, the then outermost known planet, was deviating slightly from the path predicted by Newton's laws. This wobble could mean one of two things: either Newton's laws were incomplete and began to fail at such vast distances, or there was another, as yet undiscovered planet whose gravitational pull was perturbing Uranus's orbit. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently used Newton's laws to calculate the predicted position of this hypothetical planet. And in 1846, astronomers pointed their telescopes to the predicted location and found it. Neptune was discovered, a stunning triumph for Newtonian physics and a powerful testament to the idea that the universe is governed by a deep, underlying, and comprehensible order, but at the same time that Newton's theory of gravity was celebrating its greatest triumph. A new force and a new way of thinking about the world was beginning to emerge. The self-taught English scientist Michael Faraday, a man with little formal education but an immense intuitive genius, began a series of brilliant experiments into the nature of electricity and magnetism. He showed that a moving magnet could generate an electric current in a wire, and that an electric current could, in turn, create a magnetic field. He realized that these two, seemingly separate phenomena were deeply and intimately interconnected, two sides of the same, fundamental coin. Lacking the mathematical tools to describe his discoveries in the formal language of equations, Faraday filled his notebooks with beautiful, intuitive diagrams of lines of force, invisible lines that he imagined filled the space around magnets and electric charges, guiding their interactions. In doing so, he introduced one of the most powerful and fruitful concepts in all of physics, the concept of the field. A field is a physical quantity that has a value at every point in space and time. Newton's theory of gravity could be reframed in this language. The Earth creates a gravitational field around it, and the Moon moves in response to the value of that field at its location. Faraday's field concept was a profound shift from the Newtonian picture of action at a distance. It suggested that space was not an empty void, but was filled with these invisible, energetic structures. It was the Scottish physicist and mathematician James Clerk Maxwell who would take Faraday's intuitive, physical insights and translate them into the rigorous and beautiful language of mathematics. In the 1860s, Maxwell formulated a set of 4 elegant equations that completely described all the known phenomena of electricity and magnetism. These equations, now known as Maxwell's equations, are one of the crowning achievements of 19th century physics. They showed, with mathematical certainty, that electricity and magnetism were not two separate forces, but were two aspects of a single, unified electromagnetic field. A changing electric field creates a changing magnetic field, which in turn creates a changing electric field, and so on. Maxwell realized that this self-perpetuating interplay would create a traveling wave, an electromagnetic disturbance that would propagate through space. And when he used his equations to calculate the speed of this wave, he arrived at a number that was astonishingly familiar: 300,000 kilometers per second, the speed of light. In a moment of profound insight, Maxwell realized that light itself was an electromagnetic wave. This was the second great unification in the history of physics, the unification of electricity, magnetism, and light into a single, coherent theory. Maxwell's equations also possessed a beautiful, hidden symmetry. The equations remain unchanged if you swap the electric and magnetic fields, a property known as duality. This mathematical symmetry was a deep clue that these two forces were truly two sides of the same coin. By the end of the 19th century, many physicists felt that their work was nearly complete. With Newton's laws for gravity and Maxwell's equations for electromagnetism, it seemed that all the fundamental phenomena of nature could be explained. But there were a few small, dark clouds on the horizon, a few nagging puzzles that refused to fit into this neat, classical picture. And it was from these small clouds that the great storms of 20th century physics, relativity, and quantum mechanics would be born. The stage was set for a new revolution, a revolution that would be led by a young though unknown patent clerk in Bern, Switzerland. His name was Albert Einstein, and he was about to ask a question that would change the world forever. He asked a simple, almost childlike question: what would you see if you could ride on a beam of light? According to Newton's laws of motion, you should be able to catch up to the light beam, and it would appear to you as a frozen, stationary wave. But according to Maxwell's equations, an electromagnetic wave can only exist if it is moving at the speed of light. A stationary light wave is a physical impossibility. This was a deep and profound contradiction. Einstein, with his characteristic audacity, realized that one of these two great pillars of physics must be wrong, and he placed his bet on Maxwell. He took the constancy of the speed of light as a fundamental postulate, and he worked out the consequences. If the speed of light is the same for all observers, regardless of their own motion, then something else must be relative. And that something else, he realized, was space and time themselves. In his special theory of relativity, published in 1905, Einstein showed that for a moving observer, time slows down and space contracts. The faster you move, the more pronounced these effects become. Space and time are not the absolute, unchanging backdrops of the Newtonian universe. They are a flexible, dynamic spacetime that is relative to the observer's state of motion. This led to his most famous equation, E equals mc squared, which revealed the deep equivalence of mass and energy. This formula provided the answer to a long-standing mystery: why does the sun shine? The sun and all stars are powered by the process of nuclear fusion, where a tiny fraction of the mass of hydrogen atoms is converted into a vast amount of energy. But special relativity, in solving one conflict, created another. It was incompatible with Newton's theory of gravity, which assumed an instantaneous action at a distance. Einstein spent the next 10 years grappling with this problem, and the result was his general theory of relativity, published in 1915. In this magnificent theory, gravity is no longer a force, but is the curvature of space-time itself, caused by the presence of mass and energy. Matter tells space-time how to curve, and the curvature of space-time tells matter how to move. With general relativity, Einstein had resolved the conflict between special relativity and gravity, and in doing so, he had created a new, dynamic, and geometric picture of the cosmos, a picture that would lead directly to the prediction of an expanding universe, of black holes, and of the Big Bang itself. For more than half a century, physics has been living with a profound and unresolved tension. Our understanding of the universe rests on two monumental and spectacularly successful theoretical pillars. The first is Albert Einstein's general theory of relativity, our theory of the very large, a framework that describes the universe on the grandest scales of stars, galaxies, and the expanding cosmos itself. The second is quantum mechanics, our theory of the very small, a framework that describes the bizarre and counterintuitive world of atoms, molecules, and the subatomic particles that make up all of matter. Both of these theories have been tested to an incredible degree of precision, their predictions confirmed in countless experiments, and yet they are fundamentally and seemingly irreconcilably incompatible. As they are currently formulated, general relativity and quantum mechanics cannot both be correct. For most of their work, physicists have been able to get by with a kind of pragmatic schizophrenia. If you are studying a large, heavy object, like a star or a galaxy, you use general relativity and you can safely ignore the strange effects of the quantum world. If you are studying a small, light object, like an atom or an electron, you use quantum mechanics and you can safely ignore the subtle effects of gravity. But there are places in the universe, extreme, cataclysmic environments, where this convenient separation breaks down. Inside a black hole, an immense amount of mass is crushed into an infinitesimally small point. At the moment of the Big Bang, the entire observable universe emerged from a point of unimaginable density and energy. In these realms, the world of the very large and the world of the very small collide. To understand what is happening in these ultimate frontiers of reality, We need a theory that can describe both gravity and the quantum world at the same time. We need a theory of quantum gravity. The third and most profound conflict in the history of modern physics is the conflict between its two greatest creations. The problem, at its core, is a clash of two fundamentally different pictures of reality. General relativity describes a universe where space-time is a smooth, continuous, and dynamic fabric. Its geometry warped and curved by the presence of matter and energy. Quantum mechanics, on the other hand, describes a universe that is fundamentally discrete, probabilistic, and jittery. The uncertainty principle dictates that at the smallest scales, there is an irreducible chaotic fluctuation in all physical quantities, including the energy of space-time itself. When you try to apply the principles of quantum mechanics to the smooth geometric space-time of general relativity, the mathematics breaks down. The equations yield nonsensical, infinite results. The smooth, continuous fabric of Einstein's spacetime is ripped apart by the violent, chaotic quantum fluctuations of the microscopic world. This is the central challenge that has driven theoretical physics for the last 50 years, the quest to reconcile these two, seemingly contradictory, pillars of our understanding. And it is in this quest that a new, radical, and beautiful idea has emerged. An idea that has the potential to finally resolve this deep conflict and to provide a single, unified framework for all of physics. It is the idea of string theory. For centuries, the quest to understand the ultimate nature of matter has been a journey of peeling back layers of an onion. We started with the idea of the four elements. Then we discovered atoms. Then we discovered that atoms were made of a nucleus and electrons. And then we discovered that the nucleus itself was made of even smaller particles, protons and neutrons. For a time in the mid-20th century, many physicists believed that protons, neutrons, and electrons were the final, fundamental, atomic constituents of matter. But in 1968, experiments at the Stanford Linear Accelerator Center shattered this picture. By smashing high-energy electrons into protons, physicists discovered that the proton was not a single, point-like particle, but was made up of even smaller, point-like constituents, which were given the whimsical name quarks. We now know that a proton is made of two up quarks and one down quark, while a neutron is made of two down quarks and one up quark. These up and down quarks, along with the electron, are the three fundamental particles that make up all the ordinary, stable matter in the universe we see around us. There is, at present, no experimental evidence to suggest that electrons or quarks are made of anything smaller. But the story does not end there. In our high-energy particle accelerators and in the natural cosmic ray collisions in our atmosphere, we have discovered a whole zoo of other, more exotic, fundamental particles. These particles are not found in ordinary matter because they are unstable, decaying into the more familiar, stable particles in a fraction of a second. But they are a crucial part of the fundamental structure of the universe. Physicists have discovered that all the known fundamental particles of matter can be organized into three distinct families or generations. The first family contains the up quark, the down quark, the electron, and a light, elusive, ghost-like particle called the electron neutrino. This is the family that makes up all the stable matter in the universe. The second and third families are essentially heavier and unstable, copies of the first. The second family contains the charm and strange quarks, a heavier cousin of the electron called the muon, and the muon neutrino. The third family contains the top and bottom quarks, an even heavier electron-like particle called the tau, and the tau neutrino. For every one of these particles, there is also a corresponding antiparticle, which has the same mass but opposite charge and other quantum properties. When a particle meets its antiparticle, they annihilate each other in a burst of pure energy, which is why antimatter is so rare in our universe today. This neat and experimentally confirmed picture of the fundamental particles, known as the Standard Model of particle physics, is a monumental achievement of 20th century science. But it also raises a host of deep and troubling questions. Why are there so many fundamental particles, when all the stable matter we see requires only the first family? Why are there 3 families, and not 1, or 5, or some other number, and what determines the bizarre and seemingly random hierarchy of their masses? The top quark, for example, is more than 40,000 times heavier than the up quark. The tau is over 3,500 times heavier than the electron. Are these numbers just random, accidental features of our universe, or do they point to a deeper, underlying structure that we have yet to discover? The Standard Model is also incomplete in that it does not include the force of gravity. It successfully describes the other 3 fundamental forces, the electromagnetic, the weak, and the strong, as quantum field theories, mediated by their respective force-carrying particles, but it has nothing to say about the force that governs the large-scale structure of the cosmos. The apparent arbitrariness of the particle content and the exclusion of gravity are 2 of the major shortcomings of the Standard Model. It is a wonderfully successful, but ultimately incomplete, description of reality. It is like a brilliantly detailed map of a single continent, but with no explanation for why the continent has the shape it does, and with no mention of the other continents or the vast ocean that connects them all. The quest for a deeper theory, a theory of everything, is the quest to find the map of the whole world. It is in this context, in the face of these deep and unanswered questions, that string theory emerges as a compelling, if speculative, candidate for a more fundamental description of reality. The central, revolutionary idea of string theory is deceptively simple. It proposes that the fundamental constituents of the universe are not zero-dimensional, point-like particles, but tiny, one-dimensional, vibrating loops of energy. These are the strings. From a distance, from the relatively low-energy perspective of our current experiments, these tiny strings would be indistinguishable from point particles. But if we could probe the universe with a resolution approaching the Planck length, the fundamental quantum scale of space itself, we would see that at the heart of every electron, every quark, every photon, there is a tiny vibrating filament of energy. This single, simple idea has profound and far-reaching consequences. In string theory, the rich diversity of particles we see in nature is not a consequence of a multitude of different fundamental types of matter. All particles in this picture are made of the same single fundamental ingredient, the string. The differences between them, their mass, their charge, their spin, are a consequence of the different ways this single underlying string can vibrate. It is a concept of breathtaking elegance and unity. The universe, at its most fundamental level, is not a collection of different things. It is a collection of different notes. It is a cosmic symphony, played on an orchestra of tiny, vibrating strings. An electron is a string vibrating in one pattern. An up quark is a string vibrating in another. A photon is a string vibrating in yet another. All the particles of matter and all the particles of force are just different resonant frequencies of the same fundamental entity. This is the ultimate unification. It is not just that matter and force are related. It is that they are, at their core, the same thing. They are both music. The properties of this music, the specific notes that are possible, are determined by the properties of the string itself, most notably its tension. The tension of a fundamental string is not something that can be chosen arbitrarily. It is fixed by the requirement that the theory be consistent with what we already know about the universe, particularly the strength of the force of gravity. In 1974, the physicists John Schwartz and Joel Shurik made the crucial discovery that one of the vibrational patterns of the string has the exact properties of the graviton, the hypothetical quantum particle of gravity. This was a stunning breakthrough. It meant that gravity is not an afterthought that needs to be shoehorned into the theory. It is a natural and unavoidable consequence of the theory itself. String theory is not just a theory of matter, it is also, and necessarily, a theory of quantum gravity. From this connection, one can calculate the tension of the string. The result is an unimaginably large number, about 10 to the power of 39 tons, a value known as the Planck tension. This immense tension has two key consequences. First, it means that the natural size of a string is incredibly small, on the order of the Planck length, which is why we have not yet been able to see them. Second, it means that the natural energy, and therefore, the natural mass of a vibrating string is incredibly high, on the order of the Planck mass, which is about 10 to the power of 19 times the mass of a proton. This is roughly the mass of a grain of dust, or a single bacterium, a huge mass for a fundamental particle. This raises an immediate and critical puzzle. If the natural mass scale of string theory is the Planck mass, how can it possibly explain the existence of the very light, and even massless, particles that we observe in our low-energy world, like the electron and the photon? The answer lies in the subtle and beautiful interplay between the classical energy of the string's vibration and the quantum energy of its zero-point fluctuations. Just like any quantum system, a string is subject to the uncertainty principle, and it can never be perfectly at rest. It has a certain minimum amount of vibrational energy, its zero-point energy. And it turns out that, due to a remarkable quantum mechanical cancellation, this positive zero-point energy can be almost perfectly canceled out by the negative energy associated with the string's vibrational pattern. It is like having a bank account with a huge debt and a huge credit that are almost but not quite equal. The net balance can be very small. In string theory, these delicate quantum cancellations can bring the mass of certain specific vibrational patterns down from the enormous Planck scale to the much smaller, and even zero, masses of the particles we observe. The massless graviton and photon are the result of a perfect cancellation. The light particles of the standard model, like the electron and the quarks, are the result of a near-perfect cancellation. This is a remarkable and highly non-trivial feature of the theory. However, it also highlights one of its greatest challenges: to reproduce the mass of the top quark. For example, the heaviest known fundamental particle. The cancellation between the classical and quantum energies of the string must be fine-tuned to a precision of better than 1 part in 100 million billion. Why these specific, delicate cancellations occur is not yet fully understood. It is a problem that is likely tied to the deeper, and as yet unknown, mathematical structure of the theory. But the fact that such cancellations are possible at all is what allows string theory to have a hope of describing our low-energy world. And what about the infinite number of other possible vibrational patterns? String theory predicts that there should be an infinite tower of other, much heavier particles, with masses that are integer multiples of the Planck mass. These stringy particles are far too heavy to be produced in our current particle accelerators, but they could have been produced in the fiery, high-energy environment of the Big Bang. The search for the subtle, cosmological relics of these heavy, primordial particles is one of the indirect ways that we might one day hope to test the predictions of string theory. The most profound, and perhaps most revolutionary, consequence of string theory is not its prediction of new particles, but its prediction of new dimensions. The mathematics of the theory is notoriously complex. And for decades, early versions of the theory were plagued by inconsistencies. The calculations would yield nonsensical, problematic results, like probabilities that were negative or greater than 100%. But in the early 1980s, physicists John Schwartz and Michael Green made a stunning discovery. They found that all of these mathematical inconsistencies, all of these problematic probabilities, miraculously canceled out and disappeared. But only if the universe has a very specific number of space-time dimensions. That number is 9 dimensions of space and 1 of time. This was not a feature that was put into the theory by hand. It was a demand that came out of the theory's own. Internal mathematical consistency. For a string theory to be a viable, logical theory, the universe must have 10 space-time dimensions. This is a breathtaking and deeply mysterious prediction. If the theory is correct, then the familiar three-dimensional space of our everyday experience is an illusion. We are living in a 9-dimensional world. But if this is the case, where are these other 6 dimensions? The answer, first proposed by the mathematicians Theodore Kaluza and Oscar Klein in the 1920s, is that these extra dimensions are compactified. They are curled up into a tiny, intricate geometrical shape at every single point in our familiar large-scale space. They are so small that they are completely invisible to us and to our most powerful instruments. Imagine a thin wire. From a great distance, it appears to be a one-dimensional line. But for a tiny ant walking on it, it has a second circular dimension that it can traverse. In the same way, the extra dimensions of string theory are curled up on a scale on the order of the Planck length, far too small for us to ever directly perceive. But even though they are invisible, these extra dimensions have a profound and direct impact on the physics we observe. The geometry of these curled-up dimensions, their shape, their size, their number of holes is what determines the possible ways a string can vibrate. And as we have seen, the vibrational patterns of the strings are what determine the properties of the fundamental particles. The masses and the charges of the electron, the quarks, the neutrinos, are all, in this picture, a direct consequence of the intricate 6-dimensional geometry of the hidden, compactified space. This is a stunning and beautiful idea. It suggests that the answers to the deepest questions of particle physics. Why are there 3 families of particles? Why do they have the masses they do are not to be found in the particles themselves, but in the geometry of space-time. The laws of physics are a reflection of the shape of the cosmos. The equations of string theory place tight constraints on the possible shapes of these extra dimensions. They must be a specific type of 6-dimensional mathematical object known as a Calabi-Yau manifold. There are many thousands of such shapes known to mathematicians, but it is not yet clear which, if any, corresponds to our universe. The search for the correct Calabi-Yau manifold, the one whose geometry would give rise to the specific particles and forces we see in the Standard Model, is one of the great, and as yet unsolved, challenges of string theory. It is a problem that lies at the intersection of the most advanced areas of physics and mathematics. But the implications are profound. If string theory is correct, then the universe is a far richer, more complex, and more beautiful geometric object than we ever imagined. Our familiar 3-dimensional world is just a slice, a projection, of a deeper 10-dimensional reality. And the deepest secrets of our existence are written not in the language of particles and forces, but in the silent, elegant, and hidden geometry of space itself. The greatest triumph of string theory, and the primary reason for the immense excitement and effort that has been invested in it over the last few decades, is its ability to finally resolve the deep and long-standing conflict between general relativity and quantum mechanics. The problem, at its core, is the behavior of space-time at the very smallest sub-Planck length scales. In general relativity, space-time is a smooth, continuous, geometric entity. But in quantum mechanics, the uncertainty principle dictates that at these incredibly small scales, the universe must be a place of wild, chaotic, and violent quantum fluctuations. The very fabric of space and time is thought to dissolve into a quantum foam, a roiling, turbulent sea of virtual particles and microscopic black holes. When you try to apply the smooth geometric equations of general relativity to this chaotic quantum foam, you get nonsensical, infinite results. The two theories are fundamentally at odds. String theory resolves this conflict in a beautifully simple and elegant way. By replacing the zero-dimensional, point-like particles of our previous theories with one-dimensional, extended strings, it effectively smears out the interactions between particles. In a point-particle theory, interactions happen at a single, infinitely small point in space-time. This is what leads to the problematic infinities when gravity is involved. The full concentrated force of the interaction is focused on a single point, but in string theory, interactions are not localized. When two strings collide, they do not meet at a single point. They merge and split over a small, but finite, region of space-time. This smearing out of the interaction point is a direct consequence of the string's extended nature. And it is this smearing that tames the violent quantum fluctuations of space-time. The string, because of its finite size, is not sensitive to the chaotic, sub-Planck scale details of the quantum foam. It is like trying to measure the texture of a finely grained sandpaper with your fingertip. Your fingertip is too large to resolve the individual grains, and so the surface feels smooth. In the same way, the string effectively averages over, or smooths out, the violent quantum jitter of space-time, resolving the conflict between general relativity and quantum mechanics, and eliminating the problematic infinities that have plagued all previous attempts to build a theory of quantum gravity. This resolution is not an ad hoc fix. It is a natural and unavoidable consequence of the theory's fundamental premise. But string theory's role as a unifier does not stop there. The theory has, over the years, undergone a series of its own revolutions and unifications. In the mid-1990s, in what is now known as the second superstring revolution, the physicist Edward Witten showed that the five seemingly different, consistent string theories that had been developed were not, in fact, different theories at all. They were all just different. Approximate descriptions of a single, deeper, and more mysterious underlying theory. A theory that lives in 11 space-time dimensions. He called this theory M-theory. The M is often said to stand for mystery, or mother, or membrane, because in addition to one-dimensional strings, M-theory also contains higher-dimensional objects, or brains. This discovery was a profound unification, showing that what appeared to be a fragmented landscape of different theories was, in fact, just different corners of a single, unified theoretical structure. String theory, or M-theory, is still a work in progress. It is a vast, complex, and not yet fully understood mathematical landscape. But it remains our most promising and most powerful candidate for a final unified theory of everything. It is a theory that naturally incorporates gravity into a quantum framework. It has the potential to explain the origin of all the particles and forces of nature as the different vibrational modes of a single, fundamental entity. And it does so in a way that is not just mathematically consistent, but deeply and profoundly beautiful. It is a theory that offers a vision of the cosmos as a single, unified, and harmonious whole. a cosmic symphony played on the silent, elegant, and vibrating strings of reality itself. Despite its immense theoretical elegance and its promise as a unified theory of everything, string theory is not without its critics, and it faces a number of significant challenges. The most persistent, and perhaps most serious, of these criticisms is that the theory is, at present, untestable. The fundamental scale of string theory, the Planck scale, is so incredibly small, and the energies required to probe it are so astronomically high that it is far beyond the reach of any conceivable direct experiment. The Large Hadron Collider, our most powerful particle accelerator, can probe energies that are about a quadrillion times smaller than the Planck energy. To build a particle accelerator that could directly see a string would require a machine the size of our galaxy. This has led some to argue that string theory, while a beautiful mathematical framework, may not be a true physical theory in the traditional, falsifiable sense. It is a criticism that the string theory community takes very seriously. But the lack of a direct test does not mean that the theory is completely disconnected from the observable world. There are a number of indirect and more subtle ways that we might one day hope to find evidence for string theory. One of the most promising of these avenues is in the search for supersymmetry. As we have seen, supersymmetry is a hypothetical symmetry between the two fundamental classes of particles, fermions and bosons. In a supersymmetric world, every known particle would have a superpartner with a different spin. While string theory does not absolutely require supersymmetry, all of the mathematically consistent, stable versions of the theory that have been developed so far are supersymmetric. The discovery of supersymmetric particles at the Large Hadron Collider would not be a direct proof of string theory, but it would be a major piece of circumstantial evidence, a sign that the kind of mathematical structure that underlies string theory is also at play in the real world. The search for these superpartners has, so far, come up empty, which has put some versions of supersymmetry under pressure. But the search continues at higher and higher energies. Another potential indirect test of string theory could come from cosmology. The theory of cosmic inflation, as we have seen, is thought to have been driven by a quantum field called the inflaton string theory. With its vast landscape of different possible vacuum states and its multitude of different quantum fields, provides many natural candidates for the inflaton. And different models of string-inspired inflation make different and very precise predictions for the subtle properties of the cosmic microwave background. As our measurements of the CMB become more and more precise, we may be able to distinguish between these different models and, perhaps, find a signature that points towards a string-theoretic origin for the universe. The existence of extra dimensions. Another key prediction of the theory might also leave a detectable imprint on the cosmos. Some models of brane cosmology, for example, predict that there could be subtle modifications to the law of gravity at very small, sub-millimeter scales, or that high-energy particle collisions could create tiny, fleeting black holes that would evaporate in a characteristic way. The search for these exotic phenomena is at the very frontier of experimental physics. The greatest challenge, and also the greatest promise, of string theory is to make a connection with the known and seemingly arbitrary parameters of the standard model. Why are there three families of particles? Why do they have the masses and charges that they do? In principle, the answers to these questions are encoded in the geometry of the extra compactified dimensions. The ultimate test of string theory would be to find the specific six-dimensional Calabi-Yau manifold whose geometry gives rise to the exact particles and forces we observe in our universe. And then to use the theory to predict a new, as yet unobserved phenomenon that could be experimentally verified. This is an incredibly difficult task, one that is far beyond our current mathematical and computational capabilities. But it is the goal, the dream, that drives the field forward. The journey of string theory has been a long and winding one, full of breathtaking insights, profound unifications, and formidable challenges. It is a theory that is still very much a work in progress, a beautiful and complex mathematical edifice that is still under construction. Whether it will one day prove to be the final theory of everything, the realization of Einstein's dream, or a beautiful but ultimately incorrect idea, remains to be seen. But what is certain is that the quest to understand it has already pushed the boundaries of our knowledge of physics, of mathematics, and of the very nature of reality itself. It is a testament to the enduring power of the human mind to grapple with the deepest questions of the cosmos and to dream of a universe that is, at its core, simple, elegant, and unified. Imagine a force so pervasive, so quietly influential, that it shapes the very fabric of our universe, yet remains entirely invisible to the naked eye. This unseen power is the magnetic field, a silent architect of the cosmos. It is a region in space where magnetic forces manifest, born from the simple movement of electric charges. Yet its influence is anything but simple. These fields are omnipresent, weaving a vast, interconnected web that stretches across the desolate emptiness of intergalactic space, sweeps through the majestic, spiraling arms of galaxies, and cloaks the stars, planets, and even the enigmatic black holes that populate our universe. Though we cannot see them, their presence is undeniable, their effects profound. They are the gentle hand that guides the birth of stars, the powerful current that steers high-energy cosmic rays, and the invisible shield that protects worlds like our own from the relentless fury of their suns. From the smallest molecular clouds where new stars are forged, to the largest clusters of galaxies bound together by gravity, magnetic fields are the unseen wiring of the cosmos, the silent, omnipresent force that brings order to chaos and sculpts the grand cosmic tapestry we are only just beginning to comprehend. To understand these fields is to peel back a layer of reality, to glimpse the invisible architecture that underpins all of existence. This invisible architecture is not an abstract, distant phenomenon. It is a force that is intimately connected to our own existence, a silent guardian that makes life on Earth possible. Our planet is a magnetic world, a giant, spinning dynamo that generates a powerful magnetic field extending far out into space, creating a protective bubble known as the magnetosphere. This field is not a static entity. It is a dynamic, ever-changing shield, born from the churning, convective motions of molten iron and nickel deep within the Earth's outer core. This process, known as the geodynamo, transforms the planet's rotational and thermal energy into a vast, planetary-scale magnetic field. A field that is as essential to our survival as the air we breathe and the water we drink. The sun, our life-giving star, is a source of constant and often violent activity. It continuously emits a stream of charged particles, protons, and electrons known as the solar wind. This wind travels outwards through the solar system at hundreds of kilometers per second, a relentless supersonic gale that would, if left unchecked, strip away our planet's atmosphere over geological timescales, leaving us a barren and lifeless rock, much like our celestial neighbor, Mars. But Earth's magnetic field stands as a silent sentinel against this cosmic onslaught. The magnetosphere deflects the vast majority of the solar wind particles, forcing them to flow around our planet like water around a boulder in a stream. This constant invisible battle in the space around our planet is what preserves our fragile atmosphere, protecting the delicate conditions that have allowed for the evolution and flourishing of life. We owe our very existence to this invisible magnetic shield. But the interaction between Earth's magnetic field and the solar wind is not just a story of protection. It is also a source of breathtaking beauty. Occasionally, some of the charged particles from the solar wind are trapped by the magnetosphere and are funneled down along the magnetic field lines towards the Earth's polar regions. As these high-energy particles collide with the atoms and molecules of our upper atmosphere, primarily oxygen and nitrogen, they excite them, causing them to glow. The result is one of nature's most spectacular displays, the aurora borealis in the north and the aurora australis in the south. These dancing, shimmering curtains of green, pink, and violet light are a stunning, visible manifestation of the invisible forces that govern our planet's interaction with the sun. They are a breathtaking reminder that we live within a dynamic electromagnetic environment, and that the universe, even in its most violent aspects, can create moments of profound and ethereal beauty. The auroras are the poetry of planetary physics, a silent symphony played out in the polar skies, a testament to the power and the elegance of the magnetic field that keeps our world alive. The story of planetary magnetic fields is a story of diversity. When we look at our solar system, we see a veritable zoo of different magnetic worlds, each telling a unique story of its own internal dynamics and its evolutionary history. Jupiter, the king of the planets, boasts the most powerful magnetic field in our solar system, a field that is nearly 20,000 times stronger than Earth's. This immense field is not generated by molten iron, but by a vast, deep ocean of metallic hydrogen, a strange, exotic state of matter that is formed under the crushing pressures of Jupiter's interior. This mighty magnetosphere creates intense radiation belts that are a serious hazard for any spacecraft that ventures too close, and it drives spectacular, planet-sized auroras at Jupiter's poles. It even has a profound influence on its moons, like the volcanically active Io, whose fiery eruptions are thought to be, in part, fueled by the intense magnetic and electrical interactions with its parent planet. Mars, on the other hand, tells a more cautionary tale. Today, Mars has no global magnetic field to speak of. It has only localized, remnant patches of crustal magnetism, fossilized magnetic fields that are locked into the ancient rocks of its crust. These are the ghosts of a magnetic field that Mars likely had in its distant past, when its core was still hot and molten. The loss of this global magnetic field, which probably shut down billions of years ago as the planet's core cooled and solidified, had catastrophic consequences. Without a magnetosphere to protect it, the solar wind has, over eons, stripped away the vast majority of Mars's once thicker atmosphere, transforming it from a world that may have once been warm and wet into the cold, dry, and barren desert we see today. Venus, Earth's twin in size and composition, presents another puzzle. Despite its similar size, Venus has no significant, internally generated magnetic field. This is likely due to its incredibly slow rotation. A day on Venus is longer than its year, which is not fast enough to drive the necessary churning motions in its core to create a dynamo. The study of these different planetary magnetic fields is a form of comparative planetology that allows us to understand the key ingredients necessary for creating and sustaining a habitable world. It tells us that a planet's magnetic field is not just a geological curiosity. It is a crucial component of its climate, its atmosphere, and its ultimate potential to harbor life. The Earth's magnetic field is not a static, unchanging entity. The geological record, preserved in the magnetic minerals of ancient lava flows, tells us a remarkable story. Our planet's magnetic field has, throughout its history, repeatedly and dramatically flipped its polarity. The North Magnetic Pole has become the South Magnetic Pole, and vice versa. These geomagnetic reversals are not instantaneous events. They are complex and often chaotic. processes that can take several thousand years to complete. During a reversal, the main dipole component of the Earth's field weakens significantly, and the field can become much more complex, with multiple temporary north and south poles scattered across the globe. The exact mechanism behind these reversals is still a subject of active research, but it is thought to be related to the complex, turbulent dynamics of the molten iron in the Earth's outer core. The geodynamo is not a steady, clockwork machine. It is a chaotic system, and like all chaotic systems, it is subject to sudden and dramatic shifts in its behavior. The last major reversal occurred about 780,000 years ago, and there is some evidence to suggest that we may be in the early stages of a new one, as the strength of the Earth's magnetic field has been observed to be decreasing over the last few centuries, and the North Magnetic Pole is currently wandering across the Arctic at a surprisingly rapid rate. The prospect of a geomagnetic reversal can sound alarming. What would happen to our technological civilization, so dependent on satellites and power grids, if our planet's magnetic shield were to weaken significantly for a few thousand years? And what would be the impact on life? The fossil record does not show any clear evidence of mass extinctions being correlated with past reversals, which suggests that the consequences may not be as catastrophic as one might imagine. Even during a reversal, the Earth is not left completely unprotected. A weaker, more complex magnetic field would still provide some shielding from the solar wind, and our atmosphere itself is a powerful secondary shield against cosmic radiation. But there would undoubtedly be challenges. The increased influx of energetic particles could pose a risk to our technological infrastructure and could lead to more frequent and spectacular auroral displays at lower latitudes. The study of geomagnetic reversals is a powerful reminder of the dynamic and sometimes unpredictable nature of our own planet. It is a story that is written in the rocks beneath our feet, a story of a planet that is constantly changing, constantly evolving, a story whose next chapter we may be living through right now. The journey into the heart of magnetism takes us from the familiar shield of our own planet to the grand cosmic forges where stars themselves are born. The Sun, the star at the center of our solar system, is a magnetic powerhouse. Its magnetic field is generated by a complex dynamo process, similar to Earth's, but driven by the turbulent, convective motions of the hot, ionized gas, or plasma. That makes up its interior. This solar dynamo is not a steady process. It is a cyclical one, with the Sun's overall magnetic field flipping its polarity approximately every 11 years. This 11-year cycle is the driving force behind all of solar activity. The Sun's magnetic field is not a simple, bar magnet-like dipole. It is a complex, twisted and ever-changing web of magnetic flux tubes that are constantly being stretched, sheared, and tangled by the Sun's differential rotation, the fact that its equator rotates faster than its poles. When these tangled magnetic field lines become too stressed, they can suddenly snap and reconnect, releasing a tremendous amount of energy in a violent, explosive event. These are solar flares, some of the most powerful explosions in our solar system. A large solar flare can release the energy equivalent of millions of hydrogen bombs in a matter of minutes, sending a burst of high-energy radiation and charged particles out into space. Sometimes, these magnetic reconnection events can also trigger a coronal mass ejection, a vast billion-ton cloud of magnetized plasma that is hurled out from the Sun's atmosphere at millions of kilometers per hour. If a CME is directed towards Earth, it can have a significant impact on our planet's magnetic environment, triggering powerful geomagnetic storms, beautiful auroral displays, and potentially disrupting our satellites, power grids, and communication systems. The dark, cooler regions we see on the Sun's surface, known as sunspots, are also a magnetic phenomenon. They are areas where intense, concentrated magnetic field lines are poking through the Sun's visible surface. inhibiting the flow of hot gas from the interior and causing the region to cool down. The number of sunspots on the Sun varies in a cyclical way, reaching a maximum every 11 years, in sync with the solar magnetic cycle. The study of the Sun's magnetic field is not just an academic exercise, it is a matter of practical importance, as space weather can have a real and sometimes disruptive impact on our technological society. But to truly understand the cosmic role of magnetism, we must journey even further out, into the vast, cold, and dark molecular clouds that are the stellar nurseries of our galaxy. It is here, in these seemingly serene and quiescent clouds of gas and dust, that magnetic fields play their most crucial and creative role as the silent and often unacknowledged midwives of star formation. The birth of a star begins with the slow gravitational collapse of a dense core within a molecular cloud. But this collapse is not a simple, unimpeded freefall. It is a complex and delicate dance between the inward pull of gravity and the outward push of other forces. And the most important of these is the magnetic field that threads through the cloud. The interstellar medium is not empty. It is filled with a weak, but pervasive, magnetic field. As a cloud of gas collapses under its own gravity, it pulls these magnetic field lines in with it, compressing and amplifying them. This creates a magnetic pressure that can resist the gravitational collapse, slowing it down and regulating the process. Without the moderating influence of magnetic fields, the gravitational collapse of a molecular cloud would be a much more rapid and chaotic affair, likely leading to the formation of a few very massive stars, rather than the rich diversity of stellar masses that we actually observe. The magnetic field acts as a kind of cosmic brake, ensuring that star formation is a slow, steady, and relatively efficient process. But the magnetic field does more than just resist the collapse. It also plays a crucial role in solving one of the key puzzles of star formation, the angular momentum problem. A collapsing cloud of gas, due to the conservation of angular momentum, should spin faster and faster as it shrinks, in the same way that an ice skater spins faster when she pulls her arms in. The amount of angular momentum in a typical molecular cloud core is so large that, if it were all conserved in the final star, the star would be spinning so fast that it would tear itself apart. Something must be getting rid of the excess angular momentum, and that something is the magnetic field. The magnetic field lines that are threaded through the collapsing core are also connected to the surrounding, more diffuse gas of the cloud. As the core spins up, it twists these magnetic field lines, creating a magnetic torque that transfers the angular momentum outwards from the rapidly spinning core to the more slowly rotating envelope. This process, known as magnetic braking, is incredibly efficient, and it is what allows the protostar to shed its excess angular momentum and to continue its slow, steady collapse into a stable, newly formed star. The influence of magnetism on the star formation process is visible in the very structure of the stellar nurseries themselves. High-resolution images of molecular clouds, particularly those taken in polarized light, reveal a stunning filamentary structure. These are not random, chaotic tendrils of gas. They are ordered, coherent structures, vast magnetic rivers that are shaped and confined by the interstellar magnetic field. The gas in these filaments is thought to be flowing along the magnetic field lines, channeling material from the diffuse, outer regions of the cloud into the dense, star-forming cores. The magnetic field acts as a cosmic scaffolding, guiding the flow of matter and providing the architectural blueprint for the entire star formation process. But the relationship between magnetism and the cloud is a complex one. While the magnetic field can channel the flow of the ionized component of the gas, the neutral component can, over long timescales, slowly drift across the magnetic field lines in a process known as ambipolar diffusion. This is a crucial step in the formation of a star, as it allows a dense core to decouple from the magnetic support of the larger cloud and to begin its final, inexorable gravitational collapse. The star formation process is a delicate interplay between the inward pull of gravity, the outward push of magnetic pressure, and the slow, patient drift of neutral matter through the magnetic web. The observational tools we use to study this invisible magnetic architecture are becoming increasingly powerful. By measuring the polarization of the faint, thermal radiation emitted by dust grains in molecular clouds, we can map the orientation of the magnetic field lines, as the elongated dust grains tend to align themselves with the local field. The Zeeman effect, the splitting of spectral lines in the presence of a magnetic field, provides a more direct, but much more challenging, way to measure the strength of the field itself. With new, powerful telescopes like the Atacama Large Millimeter/Submillimeter Array, we are now able to create stunning, high-resolution maps of the magnetic fields in nearby star-forming regions, providing a detailed, empirical check on our theoretical models. These observations are confirming the central and often dominant role of magnetism in the birth of stars. They are showing us a universe where the process of creation is not a simple matter of gravity, but a complex and beautiful dance between gravity, turbulence, and the silent, guiding hand of the magnetic field. The journey into the heart of cosmic magnetism takes us from the relatively gentle, organizing influence of the fields in stellar nurseries to the far more violent and spectacular realm of cosmic jets. These are some of the most powerful and enigmatic phenomena in the universe, narrow, highly collimated beams of plasma that are ejected from the vicinity of massive celestial objects at speeds approaching the speed of light. They are cosmic fire hoses of incredible power, capable of traveling for hundreds of thousands and even millions of light years, shaping the galaxies and the intergalactic medium through which they pass. And at the heart of every cosmic jet lies a powerful, twisted, and dynamic magnetic field. The formation of these jets is intimately tied to the process of accretion, the spiraling inflow of gas and dust onto a central, compact object. This can be a young, newly forming star, a dense, stellar remnant like a neutron star or a white dwarf, or, in the most spectacular cases, a supermassive black hole at the center of a galaxy. As this material spirals inwards, it forms a hot, dense, and rapidly rotating accretion disk, and it is from the inner regions of this chaotic, swirling maelstrom of plasma that the jets are born. The magnetic field is the key ingredient that channels and accelerates this outflow. The rapid rotation of the accretion disk, combined with the turbulent, convective motions within it, acts as a powerful dynamo, amplifying and twisting the magnetic field lines into a tightly wound, helical structure that extends outwards, perpendicular to the disk. These twisted, magnetic field lines act like a cosmic nozzle, a magnetic slingshot that grabs onto the charged particles of the plasma and flings them outwards at incredible speeds. The process of magnetic reconnection, where stressed and twisted magnetic field lines can suddenly snap and reconfigure themselves, is thought to be a key mechanism for releasing the immense amounts of energy that power these jets. The high-energy particles within the jets, spiraling around these powerful magnetic field lines, emit a strong, characteristic form of radiation known as synchrotron radiation. This radiation, which is most prominent at radio wavelengths, is the smoking gun signature of a cosmic jet, and it is what allows us to map their structure and to study their properties across the vast distances of the cosmos. The most powerful jets in the universe are those that are launched from the accretion disks around supermassive black holes at the centers of active galaxies. These are the quasars and radio galaxies, some of the most luminous objects in the cosmos. Their jets can be truly colossal, extending far beyond the confines of their host galaxy and plowing into the tenuous, hot gas of the intergalactic medium. As they do so, they create vast, expanding lobes of radio-emitting plasma, giant structures that can be hundreds of thousands of light-years across. These jets have a profound and transformative impact on their environment. The immense amount of energy and momentum they carry can heat up the surrounding gas, preventing it from cooling and forming new stars. This jet feedback is now thought to be a crucial mechanism in regulating the growth of massive galaxies, explaining why the most massive galaxies in the universe seem to have stopped forming stars billions of years ago. The jets from their central, supermassive black holes have effectively sterilized them, cutting off their supply of cold, star-forming gas. But jets are not just found in the most massive and exotic systems. We also see them on a much smaller scale, associated with the birth of ordinary sun-like stars. These protostellar jets, often referred to as Herbig-Haro objects, are a crucial part of the star formation process. They are thought to be the primary mechanism by which a young upforming star sheds its excess angular momentum, allowing it to continue its gravitational collapse. The outflowing jet carries away the spin, allowing the central protostar to continue to grow in mass. The study of cosmic jets is a field that brings together many different areas of astrophysics, from plasma physics and magnetohydrodynamics to general relativity and high-energy particle physics, and our observational tools are becoming increasingly powerful. With arrays of radio telescopes like the Very Large Array and the Future Square Kilometer Array, we can create stunning, high-resolution images of the jets and their interaction with their environment. With X-ray and gamma-ray telescopes in space, we can study the high-energy particles within the jets and the processes that accelerate them to near the speed of light. And with the Event Horizon Telescope, a global network of radio telescopes that can achieve an angular resolution equivalent to seeing an orange on the surface of the moon. We are now able to image the very base of the jet, right at the edge of the event horizon of a supermassive black hole. These observations are providing us with an unprecedented view of one of nature's most extreme and powerful phenomena, a phenomenon that is driven, at its core, by the beautiful, complex, and violent dance of matter and magnetism in the heart of the cosmos. The universe is a gallery of extremes, and nowhere is this more apparent than in the dense, crushed remnants of dead stars. It is in these stellar graveyards that magnetic fields can reach strengths that are almost beyond our comprehension, creating some of the most exotic and fascinating objects in the cosmos. A white dwarf is the final, evolutionary state of a star like our Sun. After it has exhausted its nuclear fuel, it sheds its outer layers to form a beautiful, glowing planetary nebula, leaving behind a hot, dense core of carbon and oxygen, about the size of the Earth, but with the mass of the Sun. Many white dwarfs have surprisingly strong magnetic fields, ranging from thousands to even billions of times the strength of Earth's magnetic field. These fields are thought to be a fossilized remnant of the magnetic field of the progenitor star, compressed and amplified during the star's collapse. These strong fields have a profound effect on the white dwarf's atmosphere, distorting the energy levels of the atoms and creating a unique and very complex spectral signature, a phenomenon known as the Zeeman effect. By carefully analyzing this spectral splitting, astronomers can map the strength and structure of the magnetic fields on the surfaces of these dead stars. But the story of magnetic compact objects gets even more extreme when we consider the fate of more massive stars. A star that is several times more massive than the Sun will end its life in a spectacular supernova explosion, its core collapsing under its own immense gravity to form a neutron star. These are objects of incredible density, packing more than the mass of the Sun into a sphere that is only about 20 kilometers in diameter. A single teaspoon of neutron star material would weigh billions of tons. As the core collapses, the conservation of angular momentum causes the neutron star to spin incredibly rapidly, often hundreds of times per second. And the conservation of magnetic flux causes its magnetic field to be amplified to truly staggering levels, typically around 1 trillion times the strength of Earth's field. If the neutron star's magnetic axis is misaligned with its rotation axis, it will sweep a powerful beam of electromagnetic radiation across space, like a cosmic lighthouse. If this beam happens to sweep across the Earth, we see it as a regular, pulsating signal, and we call the object a pulsar. Pulsars are some of the most precise clocks in the universe, and they are powerful probes of the interstellar medium and of the laws of gravity in extreme conditions. But the real drama unfolds when these magnetic, compact objects are not alone, but are part of a binary star system. If a white dwarf or a neutron star is in a close orbit with a normal companion star, its powerful gravity can pull material from the companion, creating an accretion disk of hot, spiraling gas. The interaction between this infalling material and the magnetic field of the compact object creates some of the most energetic and dynamic phenomena in the universe, in a system known as a magnetic cataclysmic variable. The magnetic field of the white dwarf is so strong that it prevents the formation of a normal accretion disk. Instead, the infalling material is channeled directly along the magnetic field lines, forming a stream or an accretion column that crashes onto the magnetic poles of the white dwarf, creating an intensely hot X-ray emitting shock. In binary systems containing a neutron star, the infalling material can accumulate on the surface, its temperature and density increasing until it triggers a runaway thermonuclear explosion, a powerful burst of X-rays that can be seen across the galaxy. But the most extreme magnetic objects in the universe are the Magnetars. These are a rare and still not fully understood type of neutron star with magnetic fields that are up to 1,000 times stronger than those of a typical pulsar, reaching strengths of up to 1,000,000,000 times that of the Earth. These are the strongest magnetic fields known to exist in the cosmos. The energy stored in these immense fields is so great that it can cause the solid crust of the neutron star to crack and shift in a violent starquake. These starquakes can trigger a catastrophic release of magnetic energy, creating a giant flare, a burst of gamma rays and X-rays that can, for a brief moment, outshine all the other sources in our galaxy combined. A giant flare from a magnetar in our own galaxy, if it were directed towards us, could have a significant impact on the Earth's upper atmosphere, even from a distance of tens of thousands of light years. Magnetars are also thought to be a leading candidate for the source of the enigmatic fast radio bursts, the powerful millisecond-long bursts of radio waves that are being detected from distant galaxies, the extreme and often violent. Behavior of these magnetic compact objects is a powerful testament to the central role that magnetism plays in the high-energy universe. They are natural laboratories for studying the behavior of matter and energy under conditions of extreme density, gravity, and magnetism, conditions that we can never hope to replicate on Earth, and they are a reminder that the universe is full of objects that are far stranger, more powerful, and more beautiful than our classical intuition could have ever imagined. Magnetars are the undisputed kings of cosmic magnetism, a rare and enigmatic class of neutron star whose magnetic fields are so titanically powerful that they warp the very fabric of reality around them. Born from the fiery death of massive stars in supernova explosions, these objects are a testament to the extremes that nature can achieve. The process of their formation is a lesson in the conservation laws of physics. As the core of a massive star collapses under its own gravity, from a size of hundreds of thousands of kilometers down to a sphere just 20 kilometers across. It conserves its angular momentum, causing it to spin up to incredible speeds, and it conserves its magnetic flux, compressing the magnetic field of the progenitor star to unimaginable densities. While all neutron stars are highly magnetized, it is thought that only those that are born with a particularly rapid initial spin can drive a powerful enough dynamo mechanism in their turbulent, convective interiors to amplify the magnetic field to the quadrillion Gauss levels that define a magnetar. This is a field that is 1,000 times stronger than that of a typical pulsar, and 1,000 trillion times stronger than the magnetic field of our own Earth. A magnetic field of this magnitude is so strong that it has profound and bizarre effects on the physics in its vicinity. It would distort the very shape of the atoms on the magnetar's surface, stretching them into long, thin needles aligned with the field lines. It would cause the vacuum of space itself to become birefringent, a quantum electrodynamical effect where the vacuum acts like a crystal, splitting a beam of light into two different polarizations. And it is the primary source of the magnetar's own extraordinary energy output. Unlike a normal pulsar, which is powered by its rotational energy, a magnetar is powered by the decay of its immense magnetic field. The energy stored in this field is so vast that it can cause the solid, crystalline crust of the neutron star to periodically crack and buckle in a violent event known as a starquake. This is analogous to an earthquake on Earth, but on a scale of energy and violence that is almost beyond comprehension. These starquakes can trigger a catastrophic and sudden reconfiguration of the external magnetic field, leading to a giant flare, a burst of high-energy gamma rays and X-rays that can release more energy in a fraction of a second than our Sun will emit in 100,000 years. In 2004, a giant flare from the magnetar SGR 1806-20, located about 50,000 light-years away on the other side of our galaxy, was so powerful that it measurably disturbed the Earth's ionosphere. If such an event were to occur from a magnetar much closer to us, the consequences could be significant. The intense and often violent activity of magnetars also explains their relatively short, observable lifetimes. The decay of their magnetic field, which powers their outbursts, also causes them to spin down much more rapidly than a normal pulsar. A typical magnetar will slow its rotation from milliseconds to several seconds in just a few thousand years. After about 10,000 years, its magnetic field has likely decayed to a point where it is no longer active, and the magnetar becomes a quiescent and largely invisible neutron star. This short lifetime is one of the reasons why magnetars are so rare. We can only see them during the brief and spectacular period of their youthful activity. The study of these extreme objects has been revolutionized by our high-energy telescopes in space, like the Chandra X-ray Observatory and the Neil Gehrels Swift Observatory. These instruments are able to detect the frequent, smaller bursts and the rare, giant flares from magnetars, allowing us to study the dynamics of their magnetic fields and the physics of their violent outbursts. These observations are providing crucial data to test our theoretical models of magnetar physics, and they are also shedding light on one of the most exciting new mysteries in astronomy, the origin of fast radio bursts. FRBs are intense, millisecond-long bursts of radio waves that are being detected from distant, extragalactic sources. Their origin is unknown, but a leading candidate is a young active magnetar. In 2020, a powerful radio burst, with properties very similar to an FRB, was detected from a magnetar within our own Milky Way galaxy, providing the first, strong, smoking gun evidence for this connection. It seems likely that at least some, and perhaps all, FRBs are the extragalactic cousins of the giant flares we see from the magnetars in our own cosmic backyard. Magnetars are more than just astronomical curiosities. They are natural laboratories for probing the limits of physics. Their immense magnetic fields allow us to study the behavior of matter and radiation under conditions of extreme energy and density, conditions that are far beyond anything we can ever hope to create on Earth. They are a window into the world of quantum electrodynamics in the strong field regime, where the vacuum itself becomes a dynamic, physical medium, and they are a powerful reminder that the universe is a place of constant and often violent transformation, a place where the death of a star can give birth to an object of such extreme and beautiful strangeness that it challenges the very boundaries of our scientific understanding. The centers of galaxies are the cosmic crucibles where the most extreme forces of nature are at play. And at the very heart of most, if not all, large galaxies lies a supermassive black hole, a gravitational behemoth with a mass of millions, or even billions, of times that of our Sun. These objects are not just passive gravitational sinks, they are dynamic, powerful engines that can have a profound and transformative impact on the evolution of their entire host galaxy. And the key to unlocking their power, the medium through which they exert their influence, is the magnetic field. A supermassive black hole, on its own, is a relatively simple object, described only by its mass and its spin. The real action happens in the accretion disk that often surrounds it, a swirling, chaotic vortex of gas, dust, and shredded stars that are being pulled in by the black hole's immense gravity. As this material spirals inwards, it is heated to millions of degrees by friction, creating an intensely luminous source of radiation that can, in the case of a quasar, outshine all the stars in the host galaxy combined. And this accretion disk is a magnetic cauldron. The turbulent, churning motions of the hot, ionized plasma in the disk act as a powerful dynamo, amplifying and tangling the magnetic field lines, creating a complex and dynamic magnetic structure that is intimately tied to the process of accretion itself. It is this magnetic field that is thought to be the primary mechanism for launching the spectacular relativistic jets that we see emerging from the centers of many active galaxies. In a process that is still not fully understood, but is likely related to the twisting of magnetic field lines by the rotating accretion disk and the spinning black hole itself, a portion of the infalling material can be grabbed by the magnetic field and accelerated outwards, perpendicular to the disk, at speeds approaching the speed of light. The Blandford-Zajec mechanism is a leading theoretical model for how this can happen. It proposes that the rotational energy of the spinning black hole itself can be extracted by the magnetic field lines that thread its event horizon, providing a powerful source of energy to drive the jets. In this picture, the magnetic field is a kind of cosmic transmission belt, converting the gravitational and rotational energy of the black hole system into the kinetic energy of a powerful, collimated outflow. We are now, for the first time in history, able to image the immediate vicinity of a supermassive black hole and to directly map the structure of its magnetic field. The Event Horizon Telescope, a global network of radio telescopes that uses a technique called very long baseline interferometry to create a virtual, Earth-sized telescope, has produced stunning images of the shadow of the supermassive black holes at the center of our own Milky Way galaxy and the giant elliptical galaxy M87. And by measuring the polarization of the radio waves emitted by the hot plasma around the black hole, the EHT has been able to create the first ever maps of the magnetic field structure right at the edge of the event horizon. These images have revealed a swirling, ordered pattern of magnetic field lines, confirming the theoretical predictions and providing a stunning, direct view of the magnetic engine that is thought to be responsible for launching the M87 jet. The influence of these black hole-driven, magnetized jets extends far beyond the galactic nucleus. They are a powerful form of feedback, a mechanism by which the central black hole can regulate the growth of its entire host galaxy. The jets plow into the interstellar medium of the galaxy, creating vast, expanding bubbles of hot gas and driving powerful shock waves that can heat up the surrounding cooler gas. This can have a profound effect on the process of star formation. Stars are born from the collapse of cold, dense molecular clouds. If the gas in a galaxy is heated up by the energy injected from a central jet, it can be prevented from cooling and collapsing, effectively shutting down or quenching the process of star formation. This jet mode feedback is now thought to be one of the key reasons why the most massive galaxies in the universe are no longer forming stars. They are red and dead, their star formation having been quenched billions of years ago by the powerful and ongoing activity of their central, supermassive black holes. The magnetic field is the crucial ingredient in this process, as it is what allows the energy and momentum of the jet to be efficiently coupled to the surrounding gas. The interplay between the growth of a supermassive black hole and the evolution of its host galaxy is one of the most active and exciting areas of modern astrophysics. It is a story of co-evolution, of a deep and intimate connection between the smallest and the largest scales of a galaxy. And it is a story that is, at its heart, a magnetic one. The magnetic fields in the accretion disk launch the jets. The jets regulate the star formation in the galaxy. The star formation provides the fuel that feeds the black hole, and the cycle continues. It is a beautiful, self-regulating cosmic ecosystem, a dance of gravity, gas, and magnetism that has shaped the appearance and the history of every large galaxy in the universe. Our own Milky Way is a relatively quiet galaxy at present, its central black hole in a state of slumber, but it has likely gone through more active jet-producing phases in its past, and it will likely do so again in the future. The study of the magnetic fields around black holes is not just about understanding these exotic, extreme objects. It is about understanding the grand, cosmic story of which we are a part. The story of how galaxies and the stars and planets within them are born, how they live, and how they die. The influence of magnetism is not confined to the dense, active environments of stars and galaxies. It extends out into the vast, tenuous, and seemingly empty spaces between them. The universe, on its largest scales, is structured as a cosmic web, an intricate, interconnected network of vast filaments of galaxies and dark matter, separated in immense, almost empty voids. And this cosmic web is not just a gravitational structure, it is a magnetized one. The space between the galaxies, the intergalactic medium, is permeated by a weak but pervasive magnetic field. The existence of these intergalactic magnetic fields is a profound and puzzling discovery. Their strength is incredibly small, typically 1 billion times weaker than the magnetic field of the Earth, but they extend over millions, and even billions, of light years, making them the largest coherent magnetic structures in the universe. The origin of these cosmic-scale magnetic fields is one of the great unsolved mysteries of modern cosmology. Where did they come from? One possibility is that they are of astrophysical origin, that they were seeded by the magnetic fields that were generated within the first stars and galaxies and then ejected into the intergalactic medium by powerful galactic winds. Outflows of gas driven by supernova explosions and the activity of central black holes over cosmic time. These ejected fields would have been stretched and sheared by the large-scale flows of the expanding universe, eventually filling the vast spaces of the cosmic web. Another, more exotic possibility is that they are of primordial origin, that they were created in the very early universe, long before the first stars and galaxies ever formed. There are several proposed mechanisms for how this could have happened. During the period of cosmic inflation, quantum fluctuations in the electromagnetic field could have been stretched to cosmological scales, creating a primordial magnetic field. Or, during one of the phase transitions of the early universe, such as the electroweak transition or the QCD transition, bubbles of a new vacuum state could have formed, and the collisions between these bubbles could have generated magnetic fields. Distinguishing between these astrophysical and primordial origin scenarios is a major goal of modern cosmology. A primordial magnetic field would have a different statistical signature than one that was generated later, and this could, in principle, be detected in the subtle patterns of the cosmic microwave background or in the large-scale distribution of galaxies. The detection of a primordial magnetic field would be a discovery of monumental importance, as it would provide a direct window into the physics of the universe in its first fleeting moments. Within the dense, hot environments of galaxy clusters, the largest gravitationally bound structures in the universe, the magnetic fields are significantly stronger than in the general intergalactic medium, reaching strengths of a few microgauss, similar to the field in our own Milky Way. These intracluster magnetic fields are thought to be amplified by the turbulent, churning motions of the hot X-ray emitting gas that fills the space between the cluster galaxies. The constant motion and merging of galaxies within the cluster acts as a powerful, large-scale dynamo, tangling and amplifying the magnetic field lines. These cluster magnetic fields play a crucial role in the physics of the intracluster medium. They can influence the transport of heat, potentially solving the long-standing cooling flow problem. The mystery of why the gas in the centers of many clusters is not cooling and forming stars as rapidly as simple models would predict. They can also accelerate cosmic ray particles to incredible energies, creating the vast, diffuse radio halos and relics that are observed in many galaxy clusters. The study of these cosmic-scale magnetic fields is incredibly challenging. They are too weak to be detected directly. Instead, we must rely on indirect methods. The most powerful of these is Faraday rotation. When a beam of polarized light, such as the radio waves from a distant quasar, passes through a magnetized plasma, its plane of polarization is rotated. The amount of this rotation depends on the strength and orientation of the magnetic field along the line of sight. By observing the Faraday rotation of many background sources seen through a galaxy cluster or a filament of the cosmic web, astronomers can create detailed, three-dimensional maps of the magnetic field structure. The next generation of radio telescopes, particularly the square-kilometer array, will revolutionize this field. With its unprecedented sensitivity and its ability to survey vast areas of the sky, the SKA will be able to map the cosmic magnetic web with a detail and a depth that is currently unimaginable. It will allow us to trace the magnetic fields from the hearts of galaxies out into the intracluster medium and along the vast filamentary structures that connect them. This will provide a completely new and fundamentally important view of the universe. It will transform our understanding of the cosmic web from a simple, gravitational structure into a dynamic, magnetized ecosystem, a place where the flow of matter and energy is governed by the complex and beautiful interplay between gravity and magnetism. The invisible, magnetic threads of the cosmos are what bind it together, and we are, for the first time, beginning to learn how to see them. The study of cosmic magnetism is a field that is driven by a constant and creative interplay between theoretical modeling, numerical simulation, and observational astronomy. Because magnetic fields are invisible, we must rely on a variety of clever, indirect techniques to detect their presence and to map their structure. One of the most important of these, as we have seen, is the observation of synchrotron radiation. When a high-energy charged particle, like an electron, spirals around a magnetic field line at a speed close to the speed of light, It emits a powerful beam of electromagnetic radiation. This synchrotron emission is a characteristic fingerprint of a magnetized, high-energy environment, and it is most prominent at radio wavelengths. By creating detailed, high-resolution maps of the synchrotron emission from objects like supernova remnants, radio galaxies, and galaxy clusters, radio astronomers can trace the structure of the magnetic fields and study the properties of the high-energy particles within them. The polarization of this synchrotron light provides even more information, as it is directly related to the orientation of the magnetic field lines. To carry out these observations, astronomers use some of the most powerful and sophisticated telescopes on Earth, ground-based radio interferometers, like the Very Large Array in New Mexico and the Low Frequency Array in Europe, consist of many individual radio antennas spread out over large distances. By combining the signals from these antennas, they can achieve an angular resolution that is equivalent to a single telescope many kilometers in size, allowing them to create incredibly detailed images of the radio sky. In the millimeter and submillimeter part of the spectrum, the Atacama Large Millimeter Submillimeter Array in Chile, a powerful interferometer situated high in the Andes Mountains, has revolutionized our view of the cold, dusty universe where stars and planets are born. ALMA's stunning images of protoplanetary disks and molecular clouds have revealed the intricate, filamentary structures that are shaped by magnetic fields, providing a direct view of the magnetic architecture of star formation. But the future of radio astronomy and of cosmic magnetism research lies with the Square-Kilometer Array. This is not a single telescope, but a next-generation global observatory, a network of thousands of radio dishes and millions of low-frequency antennas that will be spread across 2 continents, in South Africa and Australia. When completed, the SKA will be the largest and most sensitive radio telescope ever built. It will have a collecting area of a square kilometer, and it will be able to survey the sky thousands of times faster than any existing instrument. The SKA will be a magnetic field machine. Its unprecedented sensitivity will allow it to detect the faint, polarized signals from the most distant galaxies, providing a map of how the magnetic fields in galaxies have evolved over cosmic time. It will be able to map the Faraday rotation of thousands of background sources, creating a 3-dimensional tomographic map of the magnetic field in the cosmic web itself, allowing us to test our theories of the origin of cosmic magnetism. And it will be a powerful tool for studying transient magnetic phenomena, like fast radio bursts and the mergers of neutron stars.